Hey guys, for Cal BC, this is 8.8, and this is called improper integrals. Okay, so before we go on to how the improper integrals work, let's remember what the first fundamental theorem of calculus says. And it says that if a function f prime is continuous from a to b, okay, then f prime, and f prime has an antiderivative, then I can complete the definite integral, which means to do the antiderivative of f prime, which gives me f, and then do f of b minus f of a. So the key thing to notice here is that it has to be continuous, okay? So that's where the improper integrals come in, because what this is going to allow me to do, learning these rules, is that I can finish solving the integral of something that isn't necessarily continuous, okay? So bear with me, this is a little wordy initially. Solving these questions is very easy. What I do want to be very keen on is the notation, because these questions come up often in an FRQ, and if you don't write the notation properly, you will lose those points, okay? So there's two types of ways that I can have discontinuities. The first one is an infinite integral, right? So meaning that the limits, either the b on the top is infinity, the a on the bottom is negative infinity, or both cases, okay? Let's look at 1 and 2 first, okay? So assuming that it's continuous in between a and infinity, or negative infinity and b, then what you're going to do is you're going to use limit notation. If the infinity is in the spot of b, I'm going to say the limit as b approaches. It's really just technicalities, guys. So instead of b actually being infinity, we're going to put the notation that b approaches infinity. Then we can write in b. You're going to solve the f of b minus f of a, and then you're going to plug in the infinity and use your infinity rules. Same thing if negative infinity was in the bottom. Now I'm just saying that a approaches it. I can put the letter a in, finish solving it. I'm going to have an a stuck, and that's when I'm going to apply the limit. If it happens on both, you're going to pick some number c in between, and you're going to go from negative infinity to c, solve it like number 2, plus c onto positive infinity, and solve it here. So if I'm looking at this image, it's like something went forever to the left, forever to the right. I'm going to pick some value in between to chop it up and do the left half and then the right half, okay? Very easy to solve. Just make sure you're keen on these. You rewrite this to this step, and then you keep going. These 2 steps here is where you're going to lose your points if you're not neat on the notation. So the second type of improper integral is when instead of going to infinite limits, there's a discontinuity within the numbers. So let's say I do tell you like from 2 to 7, but in between 2 to 7, that function has a discontinuity. Then I'm going to approach that number either from the left or the right, okay? So this happens very often in rational functions, which is fraction functions. And the issue there is that they have an asymptote. So let's say the asymptote is at 0, and I want to know what the area under the curve is from 0 on, but 0 is an asymptote. Technically, that's a discontinuity. And then I would approach from like the left or the right of 0. And you'll see that in an example coming up. So we're going to pick up variable c. If the discontinuity is happening up by b, then we're going to approach b from either the left or the right, okay? And then you keep on with the problem as normal, just like you did in these up here, that then you end up after b minus a, you plug in the infinity, okay? Or you test that specific number from the side, okay? Same thing if the discontinuity happens at the bottom number, the a, then we approach it from the right. And then if it happens somewhere, so look, if f prime is continuous on a to b except at c, so if the discontinuity is not at one of the endpoints and it's somewhere in the middle, then I'm going to chop it up, just like I did with the infinities, at that middle point, and I can solve each of them, okay? So some last little bit of information before we start solving these is to always graph them, okay? Being able to graph them, especially for these down here with the discontinuity, not so much the infinity, it's going to give you that visual to let you know which one of these 3 to use, okay? Keep an eye out for fraction functions, okay? And then the second thing I want to let you know is sometimes this vocabulary pops up in multiple choices, and it's the word converges or diverges. You're going to see a lot of these words, a lot of this coming up when we learn series later on. But for right now, Converges just means that you get an actual number as the answer of your limit. Diverges means that either the limit does not exist or that the limit equals infinity. Okay, being that infinity is a concept and not an actual numerical value that I can get to, it counts as a diverges. Let's take a look at our first example. It says the integral from 1 to infinity of 1 over x squared. These are easy to spot because you can see the infinity on the question as the lower or upper limit, okay? So the moment I see that, I'm going to want to do a quick sketch. 1 over x squared, I know it has asymptotes at 0 and at 0. And then they're both on top, okay? If you struggle with graphing, at the beginning of my pre-cal playlist, I have a graphing video. Take a look at that. And we're going from 1, which will hit somewhere up here, all the way on to infinity. So it's all of this area that I want to be able to find. Now, believe it or not, even though this goes on forever and never touches the x-axis, infinite, there is a possibility of getting a finite number. Crazy, I know? Think about it this way. As it gets smaller, I'm adding a smaller and smaller decimal. Okay, so I'm really not adding a whole lot. I'm constantly adding a little bit less and a little bit less. So let's take a look at this notation. Okay, my first step is going to be to rewrite it, the limit. Okay, the infinity is in the spot of b as b approaches infinity. And now I can write from 1 to b. And instead of writing 1 over x squared, remember, if it's to the first power, it's ln. If it's not, I rewrite it with a negative exponent. There's step 1 of my rewrite. Step 2, I haven't plugged in an infinity, so I have to rewrite the limit until I plug it in. I'm going to do the actual antiderivative, okay, which the antiderivative here is going to be to add 1 to the exponent, which makes it x to the negative first, and divide by it, so I have a negative 1. And now I'm going from 1 to b. Still haven't plugged in that infinity, so I need to rewrite my limit. And now I'm going to do my f of b. Now I'm going to write this as 1 over x, but instead I'm plugging in my b minus my function at a, which in this case is 1. All right, now I can't do much more here. So now I'm allowed to plug in that infinity. So I'm going to say negative 1 over infinity. 2 negatives make a positive, plus 1 over 1 is 1. Okay, now if we remember from our infinity rules, if an infinity is in the denominator, a number over infinity is bottom heavy, that equals 0. Plus 1, my answer is 1, and that is considered that the limit, right, the integral, the area under the curve, converges. So I feel like the math is very easy. It's something we've been doing for a while, just a definite integral. It's really just the notation that goes along with this, okay? Let's take a look at the next one. Again, very easy to catch. I can see the infinity, all right? This is, if you would like to rewrite this, 1 to infinity, 1 over x dx. If you don't like the dx in your question, write it on the outside and you can see your function a little better. So 1 over x, I have my asymptotes at my zeros. My elbows are in opposite corners. Okay, and now again I'm going from 1, which is somewhere up there, all the way on to infinity, and it goes on forever. So visually, you might think that you're going to get the same answer, but not necessarily. So be very careful, okay? So step 1 is my notation. I need to write the limit as it's on the top. So b approaches infinity of, I'm going to write now from 1 to b of 1 over x dx. My next step is to complete the definite integral, right? So I haven't plugged in infinity. Keep writing the limit. The antiderivative here, the denominator is an exponent of 1. So this is an ln rule. Antiderivative of 1 over x is ln absolute value of x. Okay? I'm solving this from 1 to b. I won't be plugging in that limit yet, so I'm writing it again. So now I'm doing ln of b, absolute value of b, minus ln of 1. I technically don't need to write my absolute value there because I know that 1 is already positive. Okay? So now I can write out my infinity. So I'm saying ln of infinity is positive, so ln of infinity minus ln of 1. Let's remember what our ln graph looks like. So this ln graph hits right here at 1, okay? So ln of 1 is 0, okay? That's just, I have that one memorized by my graph. You can memorize it by just knowing that ln of 1 is 0. Either way. Now ln of infinity, as this function shoots out infinite to the x, right, on the right, it will continue to grow up, and always go up. So this is also infinity. Infinity minus 0 is infinity. We said that if an answer is infinity, technically does not exist, and we can write diverges. All right, let's move on to the next one. So this next one is not as obvious to see, okay? I have from 0 to 1, you don't see the infinities there, but I know that these rational functions of 1 over x to some power is going to give me some sort of an asymptote somewhere. So let's analyze that really quick. I'm going to take a minute to rewrite this as the integral from 0 to 1 of 1 over x to the 1/3 dx. If you've watched my graphing video, you know that a 1 over x graph has the asymptotes at the zeros. An odd exponent puts them in opposite corners, right? An even exponent puts them both up top, okay? So because 1 over 3 is odd, my asymptotes are at the zeros, and they are in opposite corners. Okay, so I'm going from 0, which 0 is my discontinuity issue. 0 is an asymptote. This right here is my problem area. On to infinity forever. So it's everything happening all up in here. Okay? So if 0 is my problem area, now is when I have to rewrite, okay, my limit, I'm going to pick a letter. You could pick A, B, C, whatever letter you want, okay? Because it's in the bottom, I'm going to go ahead and put A. Approaches 0, and since they want from 0 to 1, what I'm trying to find the area of is the right side, okay? And now I'm going to write this version, but I'm going to move it up with a negative exponent of x to the negative 1/3. Whoops, I forgot my integral. Okay, my integral from a to 1, right? Because I put the a is representing the 0, and the 0 was down on the bottom. And then put dx. So I'm not going to plug that in yet. I'm going to say my limit as a approaches 0 from the right. My antiderivative here, I'm going to add 1 to that exponent. If I add 1, it's like adding 3 over 3. So I'm going to say x raised to 2 over 3. Divide by my new exponent, which is 3 over 2. And I'm doing this from a to 1. Okay? Now I'm going to keep that 3 over 2 on the outside, and I'm going to say my function at b, which is my top number, minus my function at a, which is my bottom number. Okay? So 1 raised to anything is 1, so I have 3 over 2 times 1 minus, now I have 0 from the right of a function raised to 2 over 3. Okay? A function raised to 2 over 3 does not have any discontinuities. That is the whole point of this, is I want to get to something that does not have a discontinuity, so then I can analyze it. Okay? If I were to raise 0 raised to 2 over 3, there's no issue there. You could always check it out on your graphing. You just end up with 0. Okay? One quick way that you can think of this, remember that my denominator is the base. The base of this here, the denominator, is going to be the root. So it's like a cube root squared. Remember, cube roots are continuous. Squared functions are continuous. Just more ways for you to check. Okay? So I end up with 3 over 2 times 1, which gives me 3 over 2, which is my final answer. And since it gives me a number, it converges. On this next example, that dx is up there in the numerator again, so if you would like to rewrite it from 0 to 2 of 1 over x cubed dx, it might help you realize that this is a 1 over x cubed. So again, my asymptotes are at 0. 3 is odd, so they're in opposite corners. And if it's going from 0 to 2, it's my area from 0 all the way up to 2, okay? So I'm going to want to rewrite this because my discontinuity is happening right here at 0. My limit, my 0 is in the spot of a. As a approaches 0, the area that I'm looking for is on the right-hand side of the integral. Instead of writing the 0 there, I'm going to put the a to 2. And I'm going to bring that x cubed up with a negative exponent, dx. Keep writing that notation all the way up until you plug that in. And now I'm going to do my antiderivative. So if I add 1 to it, it's going to be x to the negative second, divide by my new exponent, and this goes from a to 2 now. Okay, keep writing that notation, and now I'm going to write my function, which I'm going to rewrite this one more time if you don't mind. I'm going to put negative 1/2 times 1 over x squared. So instead of saying divided by negative 2, I put times negative 1/2. And I brought that down, that x to the negative second, as 1 over x squared. Okay, this gives me the luxury that I can deal with that negative 1/2 later and just work with 1 over x squared. Okay, so one more time because I'm not plugging it in yet. I'm going to put my negative 1/2 out here and say my function at b minus my function at a. Now I can plug my 0 in. Now if I plug in a 0 from the right here, okay, 1 over, this is a squared, but it's like if I was saying 1 over x squared, is the graph that goes like this, with asymptotes on the zeros. Okay, so the question is, if I'm approaching 0, here's 0, from the right hand side, it will shoot up to infinity. Okay, so the answer of checking 0 from the right for just this function is that it will go from the right of 0 up to infinity. So I write minus infinity. Okay? Now, a number minus infinity is negative infinity. So I have negative half times negative infinity. And while a number times infinity is still infinity, a negative times a negative is going to make that positive infinity. And remember, that counts as a divergence. Okay? Let's go ahead and move on to that next one. Very similar question, but now it goes from -1 to 2. So we already saw in the last question that we rewrite this as 1 over x cubed dx. Okay? And I know that my graph has asymptotes at the zeros. Because it's cubed, it's in opposite corners. It's an odd exponent, it's in opposite corners. But now it wants us to go from -1 up to 2, which means the area from here, let me get a different color, right? In here, because this is underneath the function, right? And then here up until 2, which means that we have an issue in the middle. So we're going to have to split this. We're going to have to call this the integral from -1 up until 0, which is going to be my first problem area. And I'll already go writing this as x to the -3rd plus from 0 to 2, because 0 is a problem area. Okay? So now I'm going to solve each of these. Okay? I'm going to say here, if I'm just solving, right, this portion right here, we'll call this portion 1, which is this portion here. And then this is portion 2, which is this portion. Okay, so first this, then that. So if I'm looking here, I'm going to write the limit. My problem area is 0, which is the top, which is b. So I'm going to say as b approaches 0, now I'm approaching it from the left-hand side of the integral from -1 to b of x to the -3rd plus the limit, right? This is still my first portion. Now I'm doing my second. B is again my problem area, but B is in the bottom, so I'm going to say as a approaches 0. Now I'm finding the area to the right of 0. From a to 2, of x to the -3rd dx. So again, I'm just jotting these little marks here so you can see the first section and the second section. Okay? Rewrite your notation. My antiderivative here is the same as in the last question. So it ended up being -1 over 2 times 1 over x squared. Okay, and that now is from -1 to b plus my limit as a approaches 0 from the right. Same exact antiderivative because it's the same function. But now this is from a to 2. Okay? I can take out this -1/2. Right? And I'm going to do my function at b minus my function at a. I haven't plugged in my limit, so I still need to write it. So I'm going to say 1 over b squared minus 1 over -1 squared. Plus, do the same thing for the next. I'm going to leave my -1/2 out and say 1 over my b, which is 2 squared, minus 1 over my bottom one, which is a squared. Now in this part of the question, that 1 over b squared and 1 over a squared is, remember, just like last time, asymptotes at 0. Because it's squared, they're both on the top. So now we're really just analyzing one-sided limits, okay? So I'm going to have this negative 1/2. If I analyze 1 over a variable squared, from the left of 0, it shoots up to infinity. So this is infinity minus, this gives me 1, plus, I'm going to bring down that negative 1/2. This is 1 over 4. And then here, if I analyze 0 from the right, it also shoots up to infinity. If I distribute, a number times infinity is just infinity. Negative 1/2 times negative 1 is positive 1/2. Now, negative 1/2 times a positive 1/4 gives me negative 1 over 8. And then a number times a negative infinity is going to give me negative infinity. Sorry, this one's positive infinity. This one was negative infinity. I'm sorry about that. All right, so a negative infinity and a positive infinity cancel out. Here I just need common denominator. So I'm going to say 4 over 8 minus 1 over 8, which gives me 3 over 8 as my final answer. And this is a number, so it converges. For this last question, we have the definite integral from 0 to infinity. We can clearly see that infinity, so we know it's an improper integral. E raised to the negative x, so a regular e graph goes from the bottom and then it goes up. So the negative in the exponent just makes it flip over like this, with an asymptote here at 0. Okay, so my problem area, I'm going from 0 all the way to infinity. Obviously, infinity is my problem area. Here's 0. So I'm going to say my limit as b approaches infinity. Okay, and my integral now is from 0 to b of e raised to negative x dx. I need to do u sub. My u is my exponent. My u prime would be a negative 1. I don't have that negative 1 here, so I need to put it in. And if I do so, I need to also put it on the outside. So now I can say that this is the limit as b approaches infinity of the negative integral from 0 to b. So I'm going to write e raised to u, and then the negative 1 is going to be my u prime, which I'll write as du. Okay? On to my antiderivative. The antiderivative of e to the u is e to the u, but I need to put that u back in, okay? So if this is my u, this needs to go back in here. So I'm really writing the limit as b approaches infinity for negative, and I'm going to put e raised to negative x, and now I'll put my limit from 0 to b. Okay? Next step. My function at b minus my function at a, which in this case is 0. Remember, having a negative exponent is like writing 1 over that. So I'm going to go ahead and change that really quick. So I'm going to have 1 over e to b minus 1 over e raised to 0. Okay? And let's come up here with our work. So now I'm going to go ahead and plug that infinity. And then anything raised to 0 is 1. Okay? So if I'm analyzing now the actual e function, let's talk about what that denominator is going to be. I go up like this, right? So e raised to infinity, the further I go infinity on the x, the higher to infinity I go on the y. So e raised to infinity equals infinity. All right? And now, whenever I have infinity in the denominator, that's bottom heavy. So this equals 0. So I have negative 0 minus 1, which gives me negative times negative 1, which ends up giving me positive 1. So this converges at 1.